Without further ado, I guess I'll introduce Rob Lennox. So Rob Lennox and I have been buddies for about 10 years. We've been collaborating for that long as well. He really has a very large passion for R and also for ggplot and dplyr and stuff, and really understanding how to effectively manipulate your data. And so he's actually taught me a bunch of this stuff, and so I'm really excited for him to pass on this knowledge to all of you guys. Yeah, so without further ado, Rob Lennox.
Thank you, Kim. So when I first started in marine biology here at Dal, and I did my master's with Glenn Crossan and Steve Cook. How are the levels on that? Can you hear me in the back? Will? Okay, perfect. I was really nervous about using R in statistics and data analysis, and I remember very distinctly when I first met with Steve, and he suggested that I could potentially consider doing a master's with him. I told him that I wasn't interested because I thought that I would never have a chance to really learn R. I thought that I would never have the skills that were necessary to analyze data and do statistics, and I truly believed that. I was really nervous about it, and I turned down. I was prepared to turn down what would have been what was a life-changing opportunity because of that. And Steve convinced me that I would be all right and that I would be able to get by with whatever skills I would be able to develop. And I took it upon myself to reach out to people and spend time reading books and reading internet posts on Stack Exchange and things like that to try to develop my skills. And so I taught most of what I know about R to myself and supplemented it with code that I borrowed from other people and lessons that I learned from the internet and books. But ultimately, what I want to say about this is that I think that I didn't come into this with a particular interest or affinity for any of these programs or methods. I came into it only with an enthusiasm for the data and the systems and learning about fish and marine biology and aquatic biology. And I know that a lot of people struggle with some of these things, and it's easy to get down on oneself about the difficulty of some of these methods. But I wanted to put this workshop together particularly because I feel that it's very important to support each other in these endeavors to learn some of these methods and sharing knowledge with other people and trying to expedite the learning process for people for things that took me a really, really, really long time to learn is really important to me. So I put this workshop lecture together with the intention of being able to teach everybody a couple new things. I know a lot of people have some experience with a lot of these methods, but some people don't. I hope that everybody's able to take away a couple new things that you can apply to what you're doing. I tried to run all the code just to make sure that it all worked, and it's a huge file, so some of it's taking a long time. But this is a data set of sea trout, which are migratory brown trout that spawn in rivers, and then they migrate out to sea after a couple of years in the river, and they feed in the fjords in Norway. So these data are collected just north of where I live, in a fjord called the Ostafjord in central western Norway, just north of Bergen. And there's also Atlantic salmon smolt data. So within the data file that we have those two species, and we have detection data from throughout the fjord. So if I can get this to stop and start running through it, then I will begin the workshop. But does everybody have the code up and the data loaded in? Okay. So I'll just get started without running it for myself, and then I'll figure out how this is going to work. But the basics when I start with acoustic telemetry data is looking at the data. So the head function, and you can run that either the base R way wrapped in brackets or with the tidyverse dplyr functions. And for me, I only learned the tidyverse about 1.5 years ago. I used base R for 4.5 years, and all of a sudden I started using these tidyverse functions, and they've really changed a lot of the way that I code, and especially when it comes to telemetry data. The way you can use pipes, which are these percentage sign, greater than sign, percentage sign. These operators really allow you to chain functions together. And if you're reading code with pipes, you can just read the pipe as saying and then, because you can connect different segments of your code together with and then, with the pipe operator saying and then, and layer on multiple operations within one line, or within multiple lines, but within one chunk of code. So for a really simple example is you can wrap brackets around C-throat and use the head function, or you can simply unwrap it, use the pipe operator, and check the head. So the first 6 lines of the C-throat data frame that we have to look at that. Similarly, and I can't run it because again it's frozen because I made a terrible mistake. Similarly, if you want to subset some of your data, so if you want to look at just the 6th column, for example, in the C-throat data frame, you can use the square brackets, the comma, the C function, and then select which column you want by using the numeric index, so column 6. But using the tidyverse, you can use the select function. So the select function is as simple as using the pipe operator after the data frame name, so C-throat, the select function, and the number 6. And oftentimes when you're working with R, select seems to clash with a lot of other packages that are common for analysis. So when you're using this function, a lot of the times it won't work, and it took me a really long time to figure out the reason, but I finally figured out that you just need to specify that it's within the dplyr package. So whenever I use the select function, I always use dplyr : select, because that just ensures that it works and it's taking the select function from the correct package and not clashing. Similarly, we can do that if we want to look at the first 5 rows of the data. We could code it out with the square brackets and use the C function and look at columns or rows 1 to 5. Or we can use the slice function, which is the tidyverse equivalent. So it's just it's merely a single function. Again, you write the data frame name, you use the pipe, and you say take the C-throat data frame and then slice rows 1 to 5, and that'll give you the first 5 rows if you just want to take a look at the data. So we can use these pipe operators to perform simple tasks in R. If you want to know how many species you have, and so we have a species column in the C-throat data frame, and as I said, we know we have both C-throat and Atlantic salmon. But if you wanted to code that out to look at that, you'd have to say you'd have to use the $sign operator to pull out the species column from the C-throat data frame. You'd look at unique. So what are the unique values within that column, within that data frame? You'd have to make it a data frame and then use the function nrow, so number of rows. And that would give you 2 if I could run it, which again I still cannot, but soon I hope I will be able to. You can use the function nrow and it'll give you 2. So has everybody run that, or is everybody following along? So you see that gives you the number 2. It gives you 2 species, C-throat and salmon. But using tidyverse, using these pipes, we can unwrap that. Instead of having to wrap all these brackets around and keep track of the number of brackets that you need to have at the end, you can simply unwrap it with C-throat, pipe, distinct, which is the tidyverse equivalent of unique, species, and then nrow. So that will also give you 2. So I find it's a matter of preference, and there's an argument to be made that the base functions in R are potentially more clear, and the functions don't necessarily clash with other packages, but many of the functions that are written into dplyr allow you to look at your data and perform really important, oftentimes basic tasks, looking at your data and understanding your data very quickly and efficiently by joining them together with these pipes.
You can make a pipe too. The shortcut is Command-Shift-M.
Yeah, thank you, Jake. So you don't have to write a % greater than percentage.
Can I ask a really basic question?
Yes.
Is this CSV a combination of your metadata and the URL data?
Yes.
Okay.
Yeah. So I made like a Frankenstein file just for everybody to use. That is a good question. And if for those that didn't hear it, you can shortcut the pipe by pressing Control-Shift-M at the same time. On a Mac, it's Command-Shift-M. And that way you get that in your fingers pretty quickly, and you start hitting that fairly rapidly, and you can chain things together and do pretty good operations quite quickly. So the same thing when you're working with date times in R. It can be quite challenging to use for me anyway, to use the POSIX CT function that converts dates and times into date-time objects in R. So I use the lubridate package, which is a package that's written by the same author as the tidyverse. And lubridate provides a series of functions that really efficiently handle date-time objects. And you can even modify date-time objects that for some reason come into your data frame in different formats. So it's happened to me more than once, believe it or not, where I've had some CSVs where the format is day, month, year, and others where it's year, month, day. And when they're put together, you can't simply use a function like as POSIX CT, but you can use parse underscore date underscore time, which is a function within lubridate that I haven't given an example of here. And say that there are two potential date-time formats contained within the data frame, and you want it to find both and merge it into one, which is the native date-time object within R. So to do that, instead of just converting the date-time column within ctrout to as POSIX CT, you can unwrap it with dplyr and say ctrout data frame mutate. So mutate is a function within dplyr that allows you to modify or create new columns in your data frame. So anytime you want to create a new column, you simply use mutate and create a new column name on the left-hand side of the equals. So if I want to overwrite the date time object or column name, then I give it the exact same name as the one that's already in there. But if, for example, I wanted to create a copy of the date time column that was formatted using year, month, day, hour, minute, second, then I would simply give it a unique name and it would maintain both in the data frame. Still can't run code for myself to show you these things, but please let me know if everybody's able to follow along with that. There we go. I just needed to press the stop sign one more time. So yeah, we can format dates and times very efficiently using the dplyr package in combination with the lubridate package. Hands up who's used the lubridate package before. So pretty much everybody knows this, but a lot of people it is new to. And filtering. Filtering is probably my favorite thing to do in the tidyverse. I found filtering extremely difficult with base R, and I never really fully memorized the code. So an example of how to filter, if you want to just look at the trout detections from the ctrout data frame that we have here, using base R, you'd take the data frame name with a square bracket and which, data frame $ column name equals quote trout, and then you need the comma to indicate that you're referring specifically to columns, and that'll give you only the rows in the data frame that correspond to having trout in the species column. It's way easier to do it using dplyr. You simply unwrap it using the pipe, and you say ctrout, and then filter species equals trout. You can easily add on to this if this doesn't make a lot of sense, given that there's only two species here. God, this is really going inefficiently. There's only two species here, but if there were more, you could easily say, I want species equals trout, or species equals salmon. So within dplyr, you can easily add on new information using the and, which is just the ampersand, or the or, which is just this vertical line that I don't know the name of, which simply says I want this or that from that column. In addition, you can do this with dates and times. So if we want to filter, so let's look at okay, I'm going to subset these data because they're just way too big to go efficiently. Yeah, that's a good point. So from here out, we will refer to it as the OR operator. So here I'm using filter, or slice, sorry, to take the first 100,000 rows of the data frame so that I, oh, God damn it. So I'm just going to take the first 100,000 rows instead of like 14 million or whatever it is. And hopefully this will run a little bit more efficiently. Yeah, there we go. Okay, so I'm with you now. So we're just going to quickly look at the first few rows of our data frame, sea trout. We're going to take sea trout and make sure that we're going to mutate our date time column. Date time equals ymd underscore hms. Date time to make sure that it knows that it's properly formatted as a date. And now we're going to use the filter function that we just referred to filter month within date time equals 5. So that means we're only looking at the month of data from the month of May. And we can again chain that using our OR operator and say month date time equals 6, which was June. So that's saying we only want data from May or June for this data frame. I will comment this. And of course, everybody is familiar with the base R plotting. It's a simple command from using plot and then the $ operators to select the columns that you want. So longitude and latitude for our sea trout data. And that gives us sort of a basic outline of the array that we have in the Osterfjord outside of Bergen. But I've moved essentially all of the plotting that I do to ggplot. And hands up those who have never used ggplot at all. So there are very few. So we can start to go a little bit faster through this, I guess. Is this going a little too slowly for everybody in general? Okay. So I tend to use ggplot, which will give us essentially the same plot. But just briefly, for those who haven't used ggplot, because there are some, ggplot is all based on aesthetics, and you can identify your aesthetics within the function. So you have the ggplot function, you have the aesthetics call, and then you have your x and your y. You can add in additional pieces of information, color or fill, or you can have a z variable that can indicate depth or a color gradient. And data summaries. So this is also an extremely important one. For many years I used tapply to get data summaries. For example, if I want to look at the mean longitude that a sea trout was at by fish ID, I'd use the tapply function. And I'd get the, oh, it's a lot of NAs, it's not great. But instead, it's really easy to use this group by function. So group by basically allows you to measure any variable that you want or summarize any variable that you want based on levels of a factor in some part of your data frame. So in this data frame, we have both individual codes and species codes. So we may want to know the mean length, for example, of the trout and the salmon. So we group by species if we want to do that. But here if we want to query what the mean longitude, so the mean position, for example, of the trout of the individuals is, then we group by individual, which is a factor, and we summarize the mean longitude by naming it mean and using the function mean. And this gives us a nice, tidy data frame where we get the individual's ID and the mean longitude that it's found at throughout the data frame. So this being a toy data set or a bit of a dummy data set, some of these are not exactly of high priority or interest to actually know. They're merely examples, but you can imagine the functionality of combining group by with summarize in dplyr. And many of you probably already use it, of course, but it's something that I use probably more frequently than any other combination of dplyr codes. So we can start to build bigger plots. So I just talked about group by, and if we want to look at the sea trout database and look at how the fish, the individuals are distributed in the fjord throughout the year, we can group by month. So we're using the month function from Lubridate and calling it M. So we're saying group it by month, group it by individual, and group it by species, and give me the mean longitude with all that data. So if we run just that subset, we get the mean values for each individual, and it also gives us each individual in each month and the species that individual is from. We can plot that with points and look at the distribution by month. We can use the chord flip function from ggplot. So once you get into ggplot, you have to use the pluses to add additional layers onto the plot. So now we flip it on its side and we see months on the y-axis and the mean longitude. So this makes a little bit more sense spatially because longitude, of course, is, when you look at a map, it's along the x-axis. So you start to see the clustering of the salmon more close to the river mouth, which we'll see a little bit later, and the trout, on average, moving a little bit farther away from the river out to the fjord. Let's give these colors because red and blue don't really indicate anything about trout and salmon. Let's give them gray and gold for kind of the silver and gold color that we get for trout and salmon. So now we've got that. Let's add a box plot. So that gives us a sort of a data summary of all the so each point is an individual in each month, and the box plot gives us a summary of the distribution of individuals. And then we can also add a violin if we want. Oh God, I don't know. And the violin geome will superimpose itself. But that's kind of hard to see, so let's say color equals black. So that's an example of how we can start to see the distribution of the species. And we notice here when we look at this that the salmon appear to only be around in May. So recall that the data frame that I'm using has been subsetted for the first 100,000 values because of difficulties. So I only have data from April and May in this toy data set that I'm using here. And of course, if I recall correctly, the salmon were tagged in May, so it makes sense that they weren't there in April. We can also rerun this, essentially the same line of code, but instead of having month as a factor, oh, and it's not working on mine because I have too few values. So we'll skip that. But if it's working on yours, if you didn't subset your data to the first 100,000, you can start to see density bands to look at the distributions of the two species across months. Did anybody get that to run with their full data set? No? Okay. Yeah. Hands up if it's extremely problematic. Okay. John will give you a hand with that. This is also not going to run the next one for me, but it may run for you. Instead of having, okay, it did run for me. So instead of having density contours, you can have density polygons, where you can see the highest density of the temporal and the spatial distribution of the fish in your sort of space map. So again, here 0 is about approximately the location of the river mouth in the fjord. As you get farther to the left, you get farther out towards the ocean because we're in Norway and the coastline goes this way, basically the opposite of where we are here. And you can see that most of the trout were detected in May, relatively close to the river mouth. A subset in April, also relatively close to the river mouth. So these are sort of data exploration techniques that I often use to look at distribution through space and time. You could also use latitude and longitude instead of the temporal axis. But I think they're really effective data exploration tools.
Can you just explain what's on the x-axis right now?
Yes, that got flipped around. Thank you, Kim. Yeah, so I've modified this to show that this is the mean month along the y-axis, so 4 being April, 5 being May, and then this is the longitude value in UTM 30, so it's a meters-based projection. And all these contours and, yeah.
Is the N level based off of number of detections or number of like individuals?
It's based on number of detections.
Is there a way to reduce it to individuals?
Yeah, absolutely. You would simply do a group by and a summarize by species before you put it through that.
Okay.
Yeah. So I also did an example where we get a density contour for each individual. It probably did not work very well, given again the subsetting that I did to the data to make it run properly. Yeah, but these tools again can, and I'll show later how you can impose a map underneath this, so you can see actually how it overlies on the shape of the fjord and the river as well. But we can start to see trends in individuals. Some are using a lot more space in April and May. Some are not detected, of course. Some have very small areas of use. And these overview tools, I think, give a really nice ability to understand how the fish are moving in space and time. So again, we have, or here, we have latitude and longitude. It's no longer space and time. It's just space. So this could be superimposed on a map quite easily, which we will do. So handling spatial objects in R. So these are all spatial data, of course, and they're coming in as in the projection system UTM-33. UTM is a Universal Transmercator projection system, and it's all based on measurements in meters. But of course, a lot of the time we work in latitude and longitude, and of course in R you can easily convert between the two. So these are the tools generally that I use for working with spatial data. RGDAL all the time, RGEOS a little bit, AD habitat depending on the task. I did not get this part working, so I'm going to skip it because it is going to take, I could do it live, but it's just going to take too much time. So if we want to get our sea trout data converted from UTM, we want to probably create a new data frame called STS, so sea trout spatial. And we're going to just take the sea trout data frame and rename it. So it's essentially a copy. We're going to use the coordinates function to assign the coordinates using tilde, which is x plus y, so longitude plus latitude, which are the names in our data frame. And we'll run that. So now it's no longer a data frame. It's now a spatial points data frame. So it's a spatial object, and it's still and it has the spatial data, so it knows that the coordinates are longitude and latitude, but it doesn't know what the projection is. So you're going to have to skip a couple lines here to get down where I'm at. Change the name because I changed the name for some reason in my head. And specify that CRS, which is the coordinate reference system, is UTM-33. These coordinate reference system codes are not intuitive. I do not memorize them or know them off the top of my head. I Google them until I find what it is. Generally, you just need to find the UTM zone that your site is in, and it should correspond, but that can be a bit of a trick. So where I work here in the middle of Norway, we often use the UTM-33 coordinate reference system, but sometimes people are using GPSs that are using UTM-32, and they don't tell me, so usually I have to load in the data, play around with it, figure out what coordinate reference system they're using, and then assign it. Sometimes, of course, it's latitude, longitude, and so on. But this is the coordinate reference system call to indicate that this spatial points data frame that we've converted. So again, if we go back, we converted this data frame, C-trout, to a new one, STS. And that's a data frame. And then we indicated that there are coordinates within that file, STS. Those coordinates are called longitude and latitude. And this line of code changed the data frame into a spatial points data frame. And now, by using this proj4string function on the STS data frame and telling it which coordinate reference system we're using, it changes that spatial points data frame to a projected spatial points data frame. So before I run that, I'm going to just check what the proj4string of STS is, and it's NA, so it's not projected. It has no idea where in the world it is. It's just a series of jumbled numbers as far as the computer is concerned. But now, when I run this proj4string function with the correct coordinate reference system, and I rerun that code with proj4string STS, it tells me that it's projected to the correct UTM. But we are not interested for our purposes in using UTM. We want to use longitude and latitude. Do you have to go to ArcGIS? Do you have to go to Google Earth and find the coordinates and right-click and then copy-paste them into a file? No, you don't. You merely have to use the SP-transform function, and it really efficiently transforms any set of coordinates into the ones that you want to use. So right now, we're just going to create a new data frame again called ST, which is functionally a copy of the STS data frame or spatial points data frame that we've been working with, and give it and convert the longitude and latitude, the x and y, the spatial variables from UTM-33 into longitude and latitude. So we use the SP-transform function, we give it the data frame, and then we tell it the coordinate reference system that we want to change it to. Oh, God. So you're going to have to change, in line 141, you're going to have to change from C-trout to STS. So now, when we look at the longitude and latitude, it's no longer in UTM. It's been converted to longitude and latitude, the sort of standard Google Earth format, the one that many GPSs use. So just to recap, we had a data frame. We got it with UTM-33. We converted that data frame to a spatial points data frame. We specified the projection of the longitude and latitude that we had. We converted that to the from UTM to the long-lat format. And now we have a spatial points data frame in longitude and latitude as our spatial measurement. So now I'm going to do a quick introduction to the MarMap package, which is one of the best packages for anybody working in the marine environment. Has anybody worked with MarMap before? Okay, awesome. Yeah, John, you have? Yeah, I know. Yeah, so MarMap is the best. It's most useful for people like Jake that work in broad marine environments. It's not as useful for freshwater environments, unfortunately. But if you want to get bathymetric data and bathymetric maps, MarMap is the go-to. So I've written in the code here for creating a map. You're going to have to change some things in it because I haven't been following it, but just by running it. So I have x equals 0.5, which is just an offset of how I'm taking the of the increase and decrease in the longitude and latitude around the study site. So run that. And then we're going to create the object BGO, which stands for Bergen. It's the Bergen Airport code. And the getNOAA.bathy function. So we're going to create ST by taking the, what did we call it? The STS data frame. Oh, no, wait. We have ST. Never mind. We're going to take ST. As Tibble ST. So if you recall, ST was a spatial points data frame that we converted using SP transform. Now we're converting it back to a data frame, which is a more usable function for most of R. And if we look quickly at ST, it's a data frame. So the format of the data format that we're most used to, most accustomed to. And within getNOAA.bathy, we're saying the longitude is the minimum longitude found within that data frame. The maximum longitude is the maximum longitude found within that data frame. Same with the latitude, and then I've added the offset by increasing and decreasing by a latitude and longitude of 0.5. Latitude should have values between negative 90 and plus 90. Why is this not working? It's UTM still. MarMap. MARMAP. Okay, so I found the problem. Sorry. So, but approximately between lines 141 and 144, I had a bunch of proj4 strings in SP transform. We need to use the one in line 144 here, where we convert the ST spatial points data frame using SP transform to the CRS WGS84, which is the correct coordinate reference system to use for longitude and latitude. So you should come out, and then you just need to convert it back to the data frame. Don't need this. Using ST pipe as Tibble ST, and then it should run with the BGO function. Okay, so everybody has the map, so we can move on. So Quickly, we can look at the class of the BGO function. I have two different ways of looking at it, separated by a semicolon, so they run on the same line. You can look at class bracket BGO, or you can unwrap it with a pipe, BGO pipe class. It's the same thing, and it tells us it's of class Bathy. Okay, so we can plot BGO, and it'll give us this nice outline of where I live. I live approximately here. Yeah, right in the fjords. We can plot this using color, using base R, or we can use the auto plot function, which plots it in ggplot, or not. Unclear why not working. But the secret to plotting any spatial objects in R using ggplot, which in my opinion, is the best way to plot in R, is to use this function fortify. So any spatial polygons data frame, spatial points data frame, if you get a shape file from a colleague, you want to use this fortify function so that you can turn it into a data frame and plot it the way you want it. So I'm using fortify here and as tibble, which basically just says convert it to a special data frame. And we look at, and it has X, Y, and Z. So it gives us longitude, latitude, and depth, of course. The marmap function is giving us some terrain features, so it's giving us bathymetry, which is depth, elevation on land. And we can plot that. So we run BGO and fortify, and ggplot with the aesthetics XY and fill equals Z. And we can use geom_raster. So just subset a little bit of that. And it gives us this kind of okay image of what the land and the ocean around Bergen looks like. It's not very good. The color scale's all off, but because it's ggplot and because ggplot's super easy to work with and handle, we can start adding layers onto that. So let's add scale underscore fill underscore etopo, which is a special raster within ggplot, or within marmap. And now we get a nice terrain map here by specifying the colors a little bit better. So we can see that there's sort of a shallow coastline around Bergen. There's some low-lying areas, and then we get up into the mountains just behind Bergen. And this is the Ostafjord, so this is the area where our receivers are. And then this little valley, you can see it's a little bit lower lying through the mountains. This valley is where the Vaso River lies. So this is the home river for the sea trout and the salmon. This is obviously fairly grainy. Again, really, marmap is not really made for really high resolution, close-in plotting. It's really good if you're looking at areas like all of southern Florida or the Bahamas or Palau. But I thought it would be a good example because there's a lot of people that do have those kind of data where they're looking at large pelagics and they can get these bathymetric data and make really good maps that way. It's also, if you don't have a shape file for a large area, I do have shape files for this area, but I thought it would be easier than sharing it with everybody and everybody downloading it. I thought it would just be a good example to show this. So if we run the whole code, I've added in some extra custom features here. So on top of the geom raster and the scale fill topo, I've added labels, so X, Y, and fill. I usually now put the labels on the top instead of on the side. So I put theme legend.position equals top, and I spread it out so that the legend is more readable on the top by legend key width unit 5 centimeters. So that just makes it longer instead of all squished together. So if we take that out, you can see that it doesn't look as good. So it actually took me a while to find that specific way of elongating the legend, and now you can use that because. So you can see when it's all squished together, you can't actually see. So using that extra bit of code is quite helpful, I think. So we can start to build on this. So if we want to see where our receivers are within this fjord, we can simply add on additional items. So I've essentially copied the code that we've already ran just to run this, and added at the end of it. So you can see the last thing we have here is theme legend.position equals top, and I've added a plus, and I've added a call for a geom_point. So this is a little bit tricky, and it's something I only kind of relatively recently learned how to do to layer on additional things that are outside of the original ggplot data frame. So I'm taking data from the sea trout, the ST data frame, and adding them on as points. So geom point, the data is from the ST data frame. I'm converting that to a data frame because I think it was a spatial points data frame. So convert it to a data frame. Take the distinct longitude and latitude. That's to make sure that we're not just plotting the same point over and over and over and speed it up a little bit. So we just want all the longitudes and latitudes. And then adding the aesthetics, longitude, latitude. And this is the key. This is the key to making this work. Inherit aesthetics equals false. And this is why it took me so long to learn how to do this, because in your original ggplot call, any aesthetics that don't really appear in the secondary call will cause it to fail. But if you say inherit those aesthetics as false, then you're fine. So, yes. So if you're adding on points to a map, for example, the original, oh god damn it, bplot. The original map ggplot object is based on latitude, longitude, and depth, and that, especially that z depth, when you're adding a geom point, and it's going to want to find that depth as well, and it's not going to be in there, so it's going to fail. So you have to say, forget about what I was talking about in the initial ggplot call. Don't inherit those aesthetics. I'm going to specify my own unique aesthetics for this. It's a really weird thing to Google, which is why I had a really hard time figuring out how to do it, and eventually I found it by happenstance in someone else's code. But here we can see that we've now superimposed on this map the location in red of all the receivers that we have around the fjord and up into the river. And that's amazing. And that's the reason that we had to use that SP transform function to convert from UTM. Because we have this marmap object that's using latitude and longitude, it's not using UTM. If we were trying to superimpose the position of these receivers using UTM, they'd be way off. So we have to convert and say those UTM are equivalent to these latitudes and longitudes so that we can plot them on top of each other. So we'll move on to some interesting functions and some giant dplyr pipe chains. So you can start to see how you can put these functions together and start building a data frame that you're going to analyze or visualize or clean or use for different purposes. So we're going to take our ST object, which is now a data frame. That should be, if you just write head ST, that should be the same for everybody, correct? We all see that we have all the metadata, or all the positions and all the information for the fish in a data frame, not a spatial points data frame. So we're able to run it through this giant pipe chain. So the first thing we're going to do is make sure that we're using date times again. So I showed you how to do it already, but it's really worth emphasizing when we look at this data frame and we look at the date time, it's a factor again, because we haven't officially fully converted it. So it's just saying that this is basically a string of text. It does not know anything about the fact that this is in the year 2012. It doesn't know the time. It doesn't know anything. So you have to use the mutate, and we're going to create a new column by giving it a new name. So it's not going to be date time anymore. It's going to be DT. So if I run that quickly, we can create a new data frame. Yeah, this is too high. Or a new column within our data frame that is the properly formatted date time. We're going to get rid of our old date time by selecting out, get rid of this -2. We just want -1. We're going to select out by using the negative sign with dplyr select, date time, and this first column that's just a series of numbers. And we're going to filter out for only looking at the summer months. So for mine, because I've subsetted it, I only have April and May, so it's not as interesting. But if you only, so sea trout, for example, they spend approximately May to October, May to August, September out in the ocean, and then they'll come back to spawn in fresh water sometime between late August and early October. So if, for example, with sea trout, we were only interested in their summer residence in the fjord, we would do something like this, where we subset it by month. I'm going to take this out because it's not as interesting just by hashtagging it. I'm going to arrange by date and time. So again, we've already mutated the date-time column to create this DT object. Arrange just sorts it chronologically, so earliest to latest. If we wanted to reverse it, we would go arrange DESC date time. So I'm going to pipe, but I don't want to do that. But that's how you can arrange in reverse. And then I'm going to use the group by function to group by tag. And I'm going to use this lag function. So I want to know, by arranging it by date time, I have it chronologically. So each timestamp is now sorted, and I've grouped it by individual. So I'm telling R, for each individual, look chronologically at the series of detections. And now I'm going to use mutate to create a lag longitude and a lag latitude, basically saying, give me the last position as a new column, so that I can see right next to each other where you were before and where you were after. So L-lon is now the lag longitude, L-lat is now the lag latitude. And I'm going to filter out any detections for which the lag longitude is the exact same as the longitude. So basically, if you didn't change positions between detections, you're gone. So I'm only looking now for each individual at changes in position, which has obvious biases to it for analysis. So think critically about how you use this kind of filtering, but it'll cut down on our data frame a little bit, and it's in some cases useful. And then I want to direct your attention to these two mutate functions. So I'm using these mutate functions to create new columns in this data frame. B for bearing. Let's recall it bearing, or rename it bearing, because B is not intuitive to everybody. So bearing. So this is a measure of the directionality. So we've filtered out now sequential positions that haven't changed, and we're only looking at changes in position. And by using bearing, we want to look at the compass direction that the fish has moved at each time step. And that's in the Argos filter package. And there are two bearing functions, which is why I use Argos filter : bearing, because there's one in ArcGIS, which is open as well. And they basically do the same thing. They just have a different order of lag longitude and latitude and lag latitude. So I set this up to create a new column called bearing by going row-wise, which is sort of a bit of an esoteric function, but it's one that's required. It's basically just saying go row by row. And then I'm also creating a distance. So I want to measure the Euclidean distance between two receivers that a fish has moved between to understand exactly where they're moving. There are, again, obvious problems with this because a lot of the receivers have overlapping detections, and it can get really inflated, especially if two receivers are like 500 meters apart and they're getting detected simultaneously. It looks like they're moving 500 meters a second. So you have to be very careful with this. But in certain applications, of course, it's very important, and there's been times when this has been a really useful function for me. There's also, again, problems in these fjords where Euclidean distance will go over land. If a fish moved like that, it'll just measure the distance over land, which is incorrect. So we simply don't have time or resources right now to go into all the ways to get better, more accurate distance measurements, but this is a good introduction to some of the tools within R that you can use to spatially analyze your data, particularly to summarize how the fish are moving. So if we run all of this, we get a new overwritten data frame called ST, and let's look at it quickly. So now within ST, not only do we have receiver and tag ID and species and length and longitude and latitude and our date time that's formatted like a date time, but we also have the lag longitude, the lag latitude, the bearing of movement and the distance that they moved. Again, with biases, because I haven't filtered all this to filter out overlapping detections and things like that. Hands up if you're totally lost right now. I know we have those stickers and everything, but I do want to check in. You're having trouble? All the way up? I do need help in order to run this.
Time function is erroring.
The date time?
Yeah, for a few people, it's the same.
Okay.
So this runs, but as soon as I click this,
Okay, can I look at your ST function? Just double click on ST.
double click.
Yeah. Control Enter quickly. Okay, go to the top here. Scroll here, yeah. Okay, so you already have DT, so you're fine.
Okay.
So you should.
You can comment out the mutate line then.
Yeah.
That 184, you can comment that out with a hashtag.
Oh, okay.
And I would also get rid of that because it's going to keep
So
selecting
how would I
it.
know that? I guess.
Look at the data set like you did with the control enter.
Okay, and you could see that it was already there, and then.
Yeah.
You can't mutate something that doesn't exist.
Okay.
Yeah. Okay.
You run that block again.
Yeah, try that. Okay, who else needed help? How are you doing?
I'm waiting for this to run. I just ran it from like where we were, just from the start.
Okay.
Just, I don't know.
Yeah.
I'm gonna wait and see if that works.
Are you doing okay? Okay. Okay. So I apologize for that. Okay. Okay. How are you guys doing? Jack, you doing okay?
Oh, yeah, I fucked up all tools. So now it's not working. Oh god, I hate our tools.
Okay, that's good. You guys doing okay?
Do you know how to check your R version that our studio's using? I think so.
Yeah, that's how I usually do it. The only thing I can think of is in
Pull up your
help,
R.
I think.
Yeah,
Yeah. I don't know off the top of my head. Are you guys doing okay?
Now, yes.
Yeah.
Now? Okay, good. You guys working on it okay? Yeah, okay, awesome. How are you guys doing? You're
So lost.
really?
I have
Okay.
like almost no error experience.
Okay. Okay.
It's all good. It's been good to follow along.
Okay.
Yeah,
That's
just
good.
having some issues
You can-
with those too, so
Okay.
just, like,
But
going ahead.
potentially
Get
you
it for
can
tomorrow.
read through it after?
Yeah.
Yeah.
I'll be trying to get myself.
Okay, that's good.
My the Weavers got fucked now, like nothing is working.
Your what, sir?
The tie weavers like didn't get installed right
Okay.
from the beginning, and so now like none of I don't know why I am, but now like none of it is like going. I have to like add the alias each time, but I don't know which package each of the functions are in.
I see.
So it's like now I don't know what line I'm at.
Okay.
Anyway, so none of it is working.
Okay. Were you able to get this going, for example? You got this.
I got
Yeah.
the points on there.
Okay.
It stopped.
Okay. That's a strange problem that I can't think of how to fix off the top of my head.
Yes, I have been using at work when it's like Mac. I'm like, oh my god, I don't remember.
Yeah.
Like even like bringing the CSV, I was like C users. I was like, I don't even know what it is on here.
Yeah.
But it's because that's what's supposed to be in the box, right? Like it's
Okay. I don't have a quick fix for that, unfortunately. That's a very strange error.
okay.
But we can look at it after, potentially. Okay, so it seems as though most people are ready to move along, and we'll do that because I think we're making good time, but it's not unlimited. So we're going to look quickly at some of our process data now. So now that we've used those mutate functions to look at the bearings and look at the distances between receivers, we can look at a couple of plots of that. So looking at our data frame and grouping it by tag ID, we can mutate again and look at the cumulative distance with the cumSum function of distance, and create a ggplot with the cumulative distance, and look at how they're moving around for each species. So we can start to compare the movement of the salmon and the sea trout by looking at their the distances of their movements. Should have ran this before. So this geom step function is one of the native ggplot functions that you can use to look at sort of survival style curves, where they there we go. And we can see, has anybody else already run it? Oh God. Yeah, yes, yeah. Some of these things seem to work quite well on my computer. Let's not do that. Uh-oh. Yeah, so there we go. So we can look at how the cumulative distance of these fish has changed throughout the year. So on the x-axis we have time, which is all scrunchy for each species. So we can see the salmon, the cumulative distance moved really only starts in the middle of May after they're tagged, and they're really not making that many movements. Whereas the trout, there's a lot of intraspecific variability. So some of them, we're detecting them potentially all the way through the month from April, and they're not moving very much, whereas some are making huge cumulative movements, moving between receivers. Of course, again, that could be an artifact of one fish just sitting on the interface of two receivers, and it's looking like it's moving a lot. Again, really important to filter these data and consider how it's working before. But again, merely an example of how you can use these functions to explore how the movements are occurring. And now we can look at the bearings. So we created the bearings to look at the angles of movements between receivers for all individuals. And here we changed, in your code it should say B, but I changed it to bearing because B obviously is not informative at all. So change that to bearing in your code. And we could have our hypothesis from these data, for example, that salmon, which are migratory, so these are smolts that are leaving the river. They're hatched as eggs in the river, and then they're moving out after 2 or 3 years of feeding and growing up in the springtime. So they're moving seaward through this linear fjord, more or less linear fjord, towards the ocean. So we could make a hypothesis that the smolts are moving more unidirectionally because they're migrating, whereas the trout, which are using the fjord for feeding, should be spinning around more in circles, going back and forth. And we kind of see a little bit of that in these data. And again, I want to reiterate to be very clear that these data are not necessarily representative of what you'd actually do in an analysis, because you do a little bit more filtering before you got to this point and remove overlapping detection so that you're not having a huge influence of some receivers where they're moving back and forth a lot. But you can see how you can use this bearing function to look at average movements potentially of individuals, or different groups, to look at how they're turning within an array. And I use this density function here instead of a histogram, because when you do use the histogram, you can see very clearly that there is a huge influence of most likely 1 or 2 receivers that are close together, where the trout are just moving back and forth, or they're on the interface and it looks like they're moving back and forth. So within the data frame, when we take the bearing, it looks like they're making all these back and forth movements between 2 receivers that are way more than any other movement. They're dwarfing all the other potential bearings, whereas density just takes the average movement or more of a smooth movement and gives you these nicer looking plots. But this of course indicates very clearly that we'd have problems using these data unfiltered. So let's take a quick look at networks. What time are we at? How are you guys feeling? Yeah. All right. I don't think we'll go all the way till 5. So I'll try to get through some of this efficiently. But I think it's really important because network analyses are becoming really common. We're seeing a lot of networks in ecology, and receiver networks are really effective forms of networks for data analysis, to look at the way, especially when you have nodes, not so much when you have VPSs, but when you have a nodal system within a fjord or a lake or an ocean, you can look at movements between receivers and visualize them as networks. So in ggplot, it's very easy to make your own network diagrams simply using either geom segment or geom curve. And the way to do that is when you have your full data frame with all of your individual detection data, you can group those data by the measurements that you're interested in. So we're interested in the longitude and the latitude, as well as the lag longitude and the lag latitude, which we created a couple minutes ago using the mutate function, you'll recall, where we grouped by individual, and we took the lag, so the previous time point, latitude and longitude for each individual. So we're grouping by all these spatial data, longitude, latitude, lag latitude, and species, and then we're summarizing. So for each of these, we're taking the number. So let's run that quickly. So when I say n equals n bracket, n is just a count, and I'm naming it n because that's my personal convention for this. And so here we're not considering the influence of individuals at all. We're just on a really high level looking at whether salmon or trout are moving differently within this network. So we get the number of movements between receivers. So here we have a receiver combination, and here we have a combination of receivers that it was at before. And by building this data frame, we can get an idea of the number of movements of the two species between combinations of receivers. And quite simply, what we can do using geom_segment is draw lines between receivers to show which ones are connected. So these are the movements that the sea trout and the salmon have made within our fjord network. And that's a basic network diagram. You can also have geom_curve if you like it. I added color equals purple. And instead of straight lines connecting them, you have these curves. Of course, you probably would not overlap them the way I did. But we also have the species data, so we can facet it, so we get a side-by-side plot for each of the two species. So now we have our salmon network, so how the salmon moved among receivers compared to how the trout moved among receivers. So we can see very different network usage of the two species, and we start to see patterns in how they're using the different area that we've created for them using this receiver array. And of course, we can also add points which indicate the locations of the receivers here. So now our network diagram has both nodes, which is a network term for receivers essentially, and edges, so the connections between nodes or the movements between receivers. So just doubling back through this, we're taking our sea trout database, or our data frame. The information that we have from our data frame is the position only and the individual and the species. And using that, we take the lag of the position. So for each individual, where were you before? And where you were before indicates the movement that you've made between two receivers. So by grouping that and taking the position and the position before for the two species and summarizing by the number, we get the number of movements between receivers. And that's essentially how we've drawn this. So within our ggplot call, we have, it's a little bit different from other ggplot calls where we just have x and y, because for geom_segment and geom_curve, you need to have both xy and x_end and y_end. So a segment obviously has, a point is just a point, but a segment is 2 points. So within the aesthetic, you need to call both the start and the end of the point. So you see that I have x equals the lag lon, so where it came from, x_end equals the lon, so the longitude. Y equals the lag latitude, and y_end equals the latitude. So that's how we create our segment, and that's how this comes up. But we can also scale our points, for example, or we can scale our objects by the number. So these are just connections indicating where they've moved. But if we want to see which ones have more movements, we can add a call size equals n. So now we begin to see that it's scaling both the lines and the points using the size equals n, and it's indicating to us where more of the movements are. So for both trout and salmon, it seems that the bulk of the network usage seems to be near the river mouth, which is not too surprising, especially for my data, which I've subsetted to only include the first 100,000 lines, which are only April and May, which is the time when both the sea trout and the salmon are exiting the river and entering the fjord. So of course they're going to be using that area more frequently. And the salmon are progressively dying and not making it out of the fjord. So it makes sense that we'd have very few detections out here, because they're probably perishing somewhere in here for the most part, and a few of them are making it out here. And I have a repetition of this example where I've taken the logarithm of the number of detections for each. And yes, we can add this to our marmap object to look more spatially. So we can take bplot, which was the object that we saved as a marmap object, and we can add segments. So this again is somewhere where it's going to be, did I add it? Yeah, this is another example of where it's important to use the inherit aesthetic equals false. So we have bplot, which is just the saved marmap object, and we're adding a geom segment by saying take the sea trout data frame, group it just like we did before, so species, longitude, latitude, lag latitude, summarize the number of connections between all these points, plot the segments. We have the size again, so scale the size based on the number of detections, and scale the alpha, which is the transparency. And then very, very important, inherit aesthetics equals false. And facet it by species. And hope that it works. So yeah, so you can see that we've now superimposed this basic network diagram, and we can see that there are very clear patterns in the fjord usage by the trout, and it's very obvious that the salmon are really confined to this early part of their migration. So these data are starting to show us something about the differences in their marine habitat and survival, just based on a few simple functions. So how do we actually implement a network analysis? These are just basic network diagrams indicating movement paths and frequencies of movements. And again, I'd stress that these are not plug-and-play codes necessarily. You can't simply put in whatever data frame you have, run it, and you'll get an interesting result. You really need to think quite critically about which individuals are included, whether or not you're interested simply in grouping all individuals together. Probably you're more interested in grouping Probably you're more interested in grouping individuals together than just all the species, because this is obviously obfuscating a lot of data about individuals and just grouping a ton. So this is way overly influenced by some individuals that were survivors and movers. And if we were to plot this all by individuals instead of by species, you'd see that those plots become quite different. There's one really really good introductory package to network analysis in R called iGraph. There's a lot of important literature on graph theory that is essential to read as you're learning about network analysis and trying to implement them. But the basis is the structure of a network having edges and nodes. So you can create a network analysis with many different things, many different types of edges and nodes. You can have connections, not simply spatial connections like we have between receivers or among receivers, but you could have connections among individuals potentially. So the nodes could be individuals. If you're looking at, for example, you could be comparing different areas of the fjord and say, okay, if individuals are detected at the same time in the same place, then that's a connection via an edge, and the individuals are the nodes. But here, the simplest way to think about them is the receivers as nodes and edges connecting those nodes. So we need to begin by creating our nodes, which is a fairly simple function. We take our C-trout data frame, and then, with the pipe, we make sure it's ungrouped. We take the distinct receivers, and we add the row ID to column as the name ID. So this will become more clear once you run it. And we look at our nodes. So within our big data frame with all the sea trout and salmon data, we have hundreds of thousands of lines in the raw file. I only have 100,000. And there's lots of different receivers, but all we're interested in for the purposes of identifying the nodes is where are the receivers. So we just take the distinct receiver and give it a number from 1 to the maximum number. Yes, John?
If you were doing this across multiple receiver deployments, you could use a station or some kind of nomenclature that is more connected to geography?
Absolutely, yeah. So that's a really essential point by John, and I appreciate it very much, because receivers change, especially if you're hot swapping receivers or taking out receivers and bringing them back to warehouse. So a lot of people use station ID for this instead of receiver name, and that's something really important to keep in mind. But now we have our node list with all of our receivers and an ID number for each of our receivers. And then we're going to create our routes, so the paths through the nodes. So again, we're going to take our C-trout database, or data frame. We're going to range it by time. We're going to group it by the tag ID, the receiver. We're going to use this lag function again in a different way, where we're going to take the last receiver, not the last lat long, but essentially the same thing, so the lag of the receiver. And we're going to summarize, very similar to what we did before, the weight. Very similar to what we did in making the figure. So instead of calling it n, I've called it weight here. So weight equals n. So I'm asking it to give me, for each combination of tag ID, receiver, and previous receiver, how many individuals moved between those. And then I want to filter out any receiver location that was the same as the last receiver location, basically to say I'm not interested if it stayed at the same spot for this particular network. And the weight gives us the number of movements in between for each individual. I'm left joining it, which basically, if you're more familiar with Excel, it's similar to VLOOKUP, where I'm saying, okay, find the common value in these two data frames and smash the data together. So what I want from the nodes data frame, if you recall, if we go back here, what we want from the nodes data frame is the node ID, so the number, because we want to change. We no longer are interested in the receiver name. We want the node number. So we're using this left join to say, okay, in routes, we have receivers, but we want the node number. So we're left joining it to nodes, and then we're doing the same thing here with the lag. So we want, instead of having the lag receiver name, we want the lag receiver node number. So we run all this, and we get a nice data frame with our tag ID, our receiver, our lag receiver. So each individual, how many times did it move between a combination of receivers? So this individual moved between these two receivers one time. And these two receivers' names, or nodes numbers, are 5 and 1. Their names are here, but we want the node numbers. And then at the end, we'll just rename, because IDX and IDY is confusing, so we'll change it to to and from. So now we have our roots and we have our nodes. So we basically have our edges and our nodes or vertices. And we have our data frame with, the ID, the receiver, the lag receiver, the species that corresponds to the ID, the weight, so the number of movements in between, and the node numbers for each, from and to. And that's all you need to create a nice network using the table graph function, which I think is in iGraph. No, tidygraph. I hope I had that in my dependencies list. So I create rig, which I don't know why, but I always call my network object rig. And now we have our network object, and we can plot it really nicely using gggraph, which is a ggplot style of plotting network diagrams. So gggraph rig, geom underscore edge underscore link, alpha equals weight. Let's just look at that. What's that? That's a good question. And so now everybody's network will probably look a little bit different because of the way networks are set up. They're not spatially oriented. It's just kind of starting in a random spot and starting to draw lines. But here you see a functionally similar network diagram to the one that we drew. It's just not spatially oriented in any way. So it doesn't have any information about latitude, longitude. It's just connecting nodes with edges. Yeah, I was thinking that too. And we can.
Setting a random starting point for the randomness in it.
Yeah.
It's kind of good practice to do that for lots of different models because then you get a repeatable.
Yeah.
Okay, so good point. You can repeat it.
Gotcha. So we're gonna add in a seed using the setSeed function, which will give us a consistent set of random numbers and a consistent starting point, which should allow our graphs to look the same. We're doing on time. So as we work through this this network function with gggraph, we first added the edges. Now we can add a node underscore point. So now we see the receivers, the nodes. We have the information to split it into species, so we can add the facet by species. So we have a salmon and a trout network. But we don't really know which receiver is which is kind of challenging. So let's unhash this and add in geom underscore node underscore label. Label equals ID. Run all this. And instead of just a point, it will give us a label, which actually looks terrible. So let's get rid of the point. Ew. It's not letting me zoom it for some reason, which I don't really know. Yeah, there we go. Perfect. So that's a little bit of a different network, and it's giving us a lot of information here. So it's telling us that Salmon never visited receiver number 30. The central nodes in the network seem to be 1, 2, 3, 4, and 5, which I'm assuming are the ones that are closest to the river mouth, which corresponds with our observations from the geographical map. And that's very interesting. But networks are great visual tools, but there's also statistical and quantitative information that we can derive from networks. Those are summary statistics from networks, and those include things like diameter, degree, betweenness, and more. So degree is a relatively easy one to understand. And we can look at that within the iGraph package. So the degree of a vertex, which is a node, is the most basic structural property, the number of its adjacent edges. So essentially within a network, how many other receivers is one receiver connected to by movements between receivers. So receivers that are more central within a network will be connected to more receivers because fish are moving out to a lot of different receivers from that receiver. So degree you can think of really as centrality within a network or importance to a network. And here we can look at the degree of our network using just the degree function. And this is giving us, for each of our receivers, a measure of the degree. And if we bind that with our receiver data frame, it gives us the receiver number and the value. And then we can left join with our sea trout, group by receiver, summarized by number. And this little piece of code will give us just the total number of times that a receiver is appearing or making a detection. So let's check if the degree measure in our network analysis is correlated to the number of detections that receiver had. So we're left joining to that, renaming, and just a simple ggplot. And it looks like there is a relationship. So the higher the degree, the more detections a receiver has, which is interesting and important to think about how these very simple metrics are connected. I just want to quickly show a little bit of a more complicated approach where instead of looking just by species, let's think about the networks by individual. So I'm just wrapping this in a function called f1. It's the same exact code as above, except within here I'm adding diameter. So that's a new network summary where for each network I want to ask what is the length of the longest geodesic, which is the longest path through the network, kind of indicative of the size of the network. So networks for an individual that have a larger diameter will indicate that it's been using a wider array of receivers within the network. So this function is essentially saying, okay, make a network, or we already have the nodes, so we just need the roots. So create the roots, create the network, and give me the diameter of the network. And using this split function, we can split our sea trout data frame by tag ID and say it's now a list. Oh, this is going to go forever. It's now a list of detections for each individual, and we can run this function that we've just made for each individual, and then it'll give us the diameter of the network for each individual using the map function from per. And again, I've used the colons to indicate that I want map from per, not from the any of the geographic packages that I have open that have a map function. So very simply, by splitting by tag ID and mapping this function and turning it into a tibble and then twisting it around a little bit. I don't know why that was necessary, but I got it to work that way. I can create a data frame that has the diameter of the network for each individual based on the network analysis. And I've jammed a ton of code together here to make an example of how individual networks are related to the length of the fish. So you can have a hypothesis that larger individuals are using a broader range within the network, but of course we have two different species. So as I walk us through this, I start by splitting the C-Trout data frame. I map the network function through it so that I get the diameter of each network for each individual. I make it into a data frame. I join it to the C-Trout data to get information about the individual. I join it again with a summary of the number of detections for each individual. And with that I have a very long chain of code to give me this data frame with summary statistics for each individual. So now I'm looking on an individual basis for trout and salmon. I have the individual number, the species, the individual length, so just the measure from head to tail, the degree, which is actually the diameter, and the number of detections that it has in the network. So if I want to ask, for example, is length correlated with diameter of the network, I can make this plot. And we see, of course, that salmon, as smolts, they're much smaller than the sea trout that we tagged. So, of course, there's a little bit of a problem here. We can't exactly compare length. We have two species. So I'm going to add in this extra little piece of code where I mutate the length to scale it by species. So putting it all on a z-score scale. So for each species, the mean becomes 0 and standard deviation becomes 1, so that they're comparable. And when I plot it, it looks like that. So we see that the diameter, which it says degree here, but it's diameter. The diameter does not seem to be very, very well correlated overall or per species with the length of the fish. So larger fish don't seem to be having larger or different network use. And we can add in plus geom underscore smooth. We can add in a regression line to see how that's working. Maybe my eyes deceive me. So the question was whether or not I use permutations to simulate and randomize different networks, which is a method of sort of testing via simulation how the design of the network influences the results that you get of the network. Because, of course, the receiver placements are very biased because we tend to put receivers intentionally in places where we expect to get detections and not in places where we do not expect detections. So the usage of a network is highly skewed towards the fact that we're preferentially acquiring data where we hypothesize that we would. So I've thought for a long time about not just permutating and randomizing the networks, but also how important it is to have some semi-random or fully random array design where you're actually putting your receivers in random locations instead of biased locations. Yeah. Could you estimate detection efficiency of an array in a river by investigating the number of connections between, or comparing the number of connections between distant and nearby receivers? Is that the question, more or less?
If you had like A, B, C in a line,
yeah,
you had a lot of connections between A and C, but not nearly as many between A and B. That would mean that B isn't getting connected.
Yeah. So if you had receivers in a line A, B, and C, and you had a lot of connections between A and C, but not as many between A and B or C and B, it would indicate that there's poor detection efficiency of B. I think that's an excellent question, and I think that the answer is definitely yes. I just don't know how. To me, conceptually, it doesn't sound like a network is necessarily the best tool for it, but it would certainly be. It would certainly show you that B is something's not working very well with B. Yeah. So I'm almost out of time. I just want to show one more thing, which is something that a lot of people are interested in, which is animating plots. It was made extremely simple by the ggAnimate plot. There's still some functionality that I do not know. So this is a very basic type of animation. So we're going to just quickly make a subset of the sea trout data frame, sea trout 1, by taking out one of the individuals. And then we can do a plot similar to what we had before. So we'll take BGO, which is our MAR-map object, fortify it, make the plot, add the geom raster, add the proper scale fill, add the labels, and then we're going to add points for the receivers, just like we did before. We're just making the same exact object that we did previously. And then we're going to add points specifically for ST1. So ST1 is the data frame that we just made in the line above, where we're subsetting for one individual. And we are adding the longitude and the latitude. We're adding a different color point, and we're making sure to specify that inherent aesthetics equals false. So you can see now, this is not an animated plot, but we can see which of the receivers within the network or within the array were used by this individual. But we want the temporal aspect, which is why we want ggAnimate. So with ggAnimate, it's extremely simple to simply add transition time as a call. And you take the date of the date time, and then you can add a label. So the title equals the date, which is the frame time. Oh, no. Oh, no. And then ggAnimate will compile it all using the GIFSKI package, and you'll see it in Viewer. So many of you will already be familiar with the ggAnimate package and some of the limitations. The movements of the points will go over land. It won't follow the contours of the area in this one. I imagine a little bit more digging into it by myself. We could probably figure out how to make it follow contours. I just have not done that yet. And that'll be this will be the end of the workshop for today. So we have a couple of minutes left. If anybody has any questions or comments or wants to have a bit more of a discussion about some of the things I presented. I tried to pull out some interesting code and some interesting methods and different packages that I've worked with that I think are fun and interesting and useful for data analysis and data visualization. I hope that some of it has been useful. I know that many of you are coming here with different levels of experience. It was not possible or wise to try to create an introductory workshop for everybody, because everybody has different levels of experience. So I tried to add in different wrinkles and different new things, as well as try to cover some of the basics. I hope that everybody pulled out something interesting, even if it's a small function that you can take home and continue to play with and develop and add into your toolbox. And this is my relatively rudimentary animation that I will continue to learn how to use. So this starts to give you some of the ways that the fish are or this individual fish is moving across time. So thanks very much, everybody. I know it was a long day. I know this was a particularly long session at the end of the day. But you were all very interested, and I know everybody was following along, which I appreciate. And we have to decide what we're doing this evening now.